Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. What if the limits of today's most powerful supercomputers weren't limits at all? What if everything we believed about computation, that a problem must be solved one step at a time, that bits must be either 0 or 1, wasn't the whole story? Imagine a future where humanity no longer crawls toward answers, but leaps. In this future, we're not just building faster machines, we're redefining the very nature of thinking. Quantum computing isn't just a technological shift, it's a conceptual revolution. Instead of working with classical bits, which are either 0 or 1, quantum computers use qubits, quantum bits that can be 0, 1, or both simultaneously thanks to a phenomenon called superposition. It's like flipping a coin that stays spinning, hovering between heads and tails until you look at it. While a classical computer evaluates one possible solution at a time, a quantum computer can explore countless possibilities all at once, radically accelerating the solving of certain complex problems. But superposition is just the beginning. Now imagine you're holding two spinning coins, two qubits. If you entangle them, a bizarre and beautiful quantum phenomenon kicks in. They become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, and while it may sound like magic, it's been experimentally verified again and again. In quantum computing, this entanglement enables correlations between qubits that classical bits simply can't replicate. Together, superposition and entanglement allow quantum computers to process exponentially more information than their classical counterparts. But let's step back. Why is this such a big deal? Because there are problems, massive, world-altering problems that classical computers simply can't handle. For example, simulating the behavior of complex molecules is extremely difficult. The number of possible interactions between atoms grows exponentially as molecules get bigger. To simulate a relatively simple molecule like caffeine, a classical supercomputer would require more bits than there are atoms in the observable universe. But a quantum computer could, in principle, simulate it directly, atom by atom, interaction by interaction, using quantum systems to model other quantum systems. That opens the door to custom-designed drugs, advanced materials, and clean energy breakthroughs. Consider this. In 2019, Google's quantum team used a 53-qubit quantum processor called Sycamore to perform a highly specific mathematical task in just 200 seconds. Their estimate? A classical supercomputer would have taken 10,000 years to complete the same task. This event marked what scientists call quantum supremacy, the first time a quantum device clearly outperformed any classical machine on a defined problem. Critics debated the practical value of the task, but the symbolic victory was enormous. It was as if humanity had just taken its first powered flight, brief, imperfect, but undeniably real. Yet, quantum supremacy is only the beginning. The real goal is quantum advantage, the point where quantum computers consistently outperform classical ones on useful real-world problems. And to get there, we need more than just a few dozen qubits. We need millions, all operating with near-zero error rates. That's a huge challenge. Qubits are delicate. They're easily disturbed by noise from their environment. Vibrations, stray electric fields, even cosmic rays. When disturbed, they lose their quantum state, a process known as decoherence. To prevent this, quantum computers are often housed in cryogenic environments just above absolute zero, colder than outer space. Engineers and physicists are working tirelessly to solve this. They're building more stable qubits out of superconducting circuits, trapped ions, and topological materials. They're designing quantum error correction protocols, algorithms that detect and fix mistakes as they happen, much like your phone. Autocorrects a typo mid-text. And they're innovating new ways to interconnect qubits, ensuring they can talk to one another without introducing more errors. Governments and tech giants have taken notice. The United States passed the National Quantum Initiative Act in 2018, pouring hundreds of millions of dollars into quantum research. China, the European Union, and Canada have launched their own national programs. Companies like IBM, Intel, Google, and Honeywell are all racing to build practical quantum machines. Startups like IonQ, Rigetti, and PsiQuantum are betting on novel approaches that could leapfrog traditional architectures. It's not just an arms race, it's a minds race. But quantum computing isn't just about faster processors. It could also shatter the foundation of modern cybersecurity. Most of today's internet encryption is based on the difficulty of factoring large numbers, a task that would take classical computers centuries. But a quantum algorithm discovered by mathematician Peter Shor in 1994 could, in theory, break these codes in seconds. That's why there's a global scramble to develop post-quantum encryption, new cryptographic systems that can resist quantum attacks. In other words, we're preparing for a future where quantum computers don't just make our current systems obsolete, they make them vulnerable, and the applications go far beyond cryptography. Financial institutions are exploring quantum algorithms to optimize high-frequency trading strategies. Airlines are investigating how to use them to streamline global logistics networks. Climate scientists hope to model chaotic weather systems in real time. Physicists are even using quantum simulations to explore the behavior of black holes and exotic phases of matter. In short, quantum computing could become the universal translator between raw data and deep insight, a tool not just for solving equations, but for understanding reality itself. Every great journey starts with a few brave explorers, and right now, Cosmic Whispers is just beginning. If you've made it this far, you're one of the pioneers, curious, courageous, and captivated by the unknown. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. So, where does this extraordinary story begin? Who were the minds that first dared to think beyond Newtonian physics and classical mechanics? In the early 20th century, a group of bold scientists stood at the edge of knowledge and peered into the quantum abyss. Their discoveries would not only transform physics, they would lay the groundwork for the most revolutionary computing paradigm in human history. The birth of quantum computing didn't begin with machines. It began with mysteries, cosmic riddles that the classical world simply couldn't answer. At the turn of the 20th century, the universe behaved in ways that baffled even the brightest minds. Light acted like both a wave and a particle. Electrons refused to orbit atoms the way planets orbit the sun. Energy came in strange, indivisible packets. The old rules, the classical rules, were breaking down, and something extraordinary was emerging from the cracks. It all started in 1900, when a German physicist named Max Planck tried to solve what was known as the ultraviolet catastrophe. According to classical physics, a black body, an object that absorbs and emits radiation perfectly, should emit infinite energy as its temperature increased. But reality disagreed. Planck proposed a radical solution. Energy is not continuous, but quantized. It comes in discrete chunks or quanta. This simple idea laid the foundation for quantum theory. Planck didn't know it then, but he had just opened Pandora's box. Soon after, in 1905, a young patent clerk named Albert Einstein took Planck's quanta further. He suggested that light itself was made of particles, later called photons, and that these particles could knock electrons loose from metal, explaining a phenomenon known as the photoelectric effect. This wasn't just revolutionary, it was heresy to classical physics, but experiments confirmed it. For this, Einstein would win the Nobel Prize, not for relativity, but for the photoelectric effect, the spark that ignited quantum physics. As the years unfolded, the quantum world became stranger. Niels Bohr introduced the idea that electrons occupy fixed energy levels within atoms and can only jump between them by absorbing or emitting a quantum of energy. Bohr's atomic model explained hydrogen's spectral lines perfectly, but it couldn't explain more complex atoms. Then came Louis de Broglie, who suggested that matter, like light, has wave-like properties. Suddenly, electrons weren't just particles. They were waves that could interfere, diffract, and behave probabilistically. By the 1920s, a new generation of physicists had taken the stage. Erwin Schrödinger, an Austrian theoretical physicist, devised the now famous Schrödinger equation, a mathematical wave function that described the behavior of particles. In this strange new view, particles didn't have precise locations. Instead, they existed in clouds of probability, where a particle was likely to be depended on the square of its wave function, and when you measured it, the wave function collapsed and the particle chose a definite position. Reality, it seemed, only resolved itself when observed. Then came Werner Heisenberg, whose uncertainty principle shattered any last hopes of determinism. He showed that the more precisely you knew a particle's position, the less precisely you could know its momentum, and vice versa. This wasn't due to experimental error. It was a fundamental property of nature. The universe, at its most granular level, was governed by uncertainty. But quantum mechanics wasn't just weird, it was successful. It explained atomic spectra, chemical bonds, radioactive decay, and even why the sun shines. Yet it also sparked fierce debate. Einstein famously resisted the probabilistic nature of quantum theory, saying, "God does not play dice with the universe." In response, Bohr dryly replied, "Stop telling God what to do." This debate culminated in the famous EPR paradox in 1935, where Einstein, Podolsky, and Rosen argued that quantum theory must be incomplete because it allowed spooky action at a distance. That spooky action, now known as entanglement, would later become the cornerstone of quantum computing. As the world hurtled toward mid-century, another giant emerged, John von Neumann. A mathematical prodigy, von Neumann formalized quantum theory and laid the foundation for modern computing. While he never built a quantum computer, his architecture, the idea of a stored program machine with a central processor, would influence the development of classical computers and eventually quantum ones. But it wasn't until the 1980s that the idea of quantum computing truly came alive. Physicist Richard Feynman, known for his charisma and insight, posed a challenge to the scientific world. Classical computers, he argued, were fundamentally ill-suited to simulate quantum systems. "Nature isn't classical," he said. "If you want to make a simulation of nature, you'd better make it quantum mechanical." His proposal: build a machine that used the principles of quantum mechanics to simulate other quantum systems. A computer that thinks in quantum, a computer made of qubits. This idea was a spark in dry brushwood. In the years that followed, the concept matured. In 1985, British physicist David Deutsch formalized the idea of a universal quantum computer, a theoretical machine that could simulate any physical process. Quantum computing had transitioned from a thought experiment into a rigorous mathematical framework. By the early 1990s, groundbreaking algorithms began to emerge. Peter Shor's algorithm for factoring large numbers and Love Grover's search algorithm demonstrated that quantum computers could, in theory, outperform classical ones by enormous margins. But turning theory into hardware, that was a challenge of a different magnitude. Creating a single qubit is hard. Creating 10 stable, entangled, and controllable qubits is heroic. Creating hundreds or thousands is a technological moonshot. Over the past 3 decades, researchers have explored numerous approaches: superconducting circuits, trapped ions, quantum dots, topological qubits, and photonics. Each has its strengths and weaknesses. Some qubits are easier to manipulate. Others are more stable, but none are perfect, not yet, and yet progress marches forward. From Schrödinger's pencil-sketched equations to IBM's quantum cloud platform, the evolution is staggering. Today, anyone with internet access can run experiments on real quantum machines, devices chilled to near absolute zero, whispering in the language of quantum logic gates. It's a long way from the chalkboards of Copenhagen and Göttingen. What makes quantum computing so captivating isn't just its power, it's the mystery. Every breakthrough feels like opening a door into a deeper reality, one that's always existed, but was hidden behind the veil of classical understanding. In quantum computing, we're not just building machines, we're tapping into the rules of the cosmos itself. And the journey is only beginning. Picture this: a gleaming lab somewhere deep within the heart of Silicon Valley. Cryostats the size of oil drums hum softly as superconducting chips sit suspended in chambers colder than outer space. A tangle of golden wires, delicate as a spider's web, feeds into a shimmering processor no larger than a coin. The room doesn't look like the birthplace of a revolution, but here, in this frozen chamber, the quantum age is being forged, one fragile qubit at a time. Welcome to the front line of quantum hardware, where theory meets engineering and every nanometer counts. At the core of any quantum computer lies its qubits, and not all qubits are created equal. While classical bits are made from simple on-off transistors, qubits demand a subtler, stranger form. The challenge: creating physical systems that can embody the strange rules of quantum mechanics and be precisely manipulated by engineers and algorithms. One of the leading approaches is superconducting qubits, the kind used by tech giants like Google and IBM. These qubits are built from tiny electrical circuits made of superconducting materials, substances that conduct electricity with zero resistance when cooled to extremely low temperatures. When configured in specific loops, these circuits can exhibit quantum behaviors like superposition and entanglement. Here's how it works. Each superconducting qubit contains a Josephson junction, a sandwich of insulating material between two superconductors. When a microwave pulse is applied, it nudges the circuit into one quantum state or another, or both at once. These pulses are like a language, quantum gate operations, that control how qubits interact. In 2019, Google used its 53-qubit superconducting processor, Sycamore, to achieve quantum supremacy. It wasn't a general-purpose computer, but it proved that quantum mechanics could be harnessed at scale, even if only briefly. Another major player? Trapped ion qubits. Imagine a string of individual atoms like beryllium or ytterbium suspended in space using electric and magnetic fields. These atoms are cooled with lasers and manipulated by firing precisely tuned beams of light. Each atom represents a qubit, and its internal energy levels define the 0, 1, or quantum blend of the two. This technique offers astonishing precision and coherence times. The qubits remain stable for much longer than in most superconducting systems. Companies like IonQ and Quantinuum are pioneering this field, promising systems that scale with atomic perfection. Then there's quantum photonics, where qubits are represented not by atoms or electrons, but by photons, particles of light. These photons travel through optical circuits etched into chips, guided by mirrors, beam splitters, and detectors. Photonic quantum computing holds an enormous advantage. Photons barely interact with their environment, meaning they're far less prone to decoherence. Plus, photonic chips could theoretically run at room temperature, making them easier to deploy. Australia's PsiQuantum and Canada's Xanadu are banking on this approach, racing to deliver fault-tolerant quantum machines using the speed of light itself. Yet another contender is the topological qubit, perhaps the most exotic of all. Based on theoretical particles called anyons, quasi-particles that exist only in two dimensions, topological qubits promise extreme robustness against noise. They rely on the braiding of particle paths in spacetime, forming quantum information that's inherently protected from decoherence. Microsoft has poured years and resources into making topological qubits a reality. If successful, they could be the most stable and scalable of all. But for now, they remain largely experimental, a dream at the edge of physics. Each approach carries its own trade-offs. Superconducting qubits are fast but noisy. Trapped ions are precise but slow. Photons are robust but hard to entangle. Topological. Qubits offer resilience but lack proven hardware. No single method has yet emerged as the definitive winner. And perhaps that's the point. We're in a golden age of experimentation. This isn't a sprint to the finish. It's a multi-front race across a vast and shifting terrain. Of course, building the qubits is only half the battle. The real nightmare lies in quantum error correction. Because qubits are so fragile, any stray vibration, cosmic ray, or thermal fluctuation can collapse their delicate state. Unlike classical computers, Where errors are rare and easy to fix, quantum errors are persistent and subtle. One corrupted qubit can ruin an entire computation. To fix this, scientists have developed ingenious techniques. One of the most promising is the surface code, which spreads quantum information across many physical qubits to form one logical qubit. Think of it like protecting a secret message by hiding it across 1,000 glass tiles. If a few shatter, the message can still be recovered. But this comes at a cost. Today's machines need thousands of physical qubits to make just a few reliable logical ones. That's why companies are investing in quantum scaling, the art of building systems with hundreds of thousands, even millions of qubits. To reach that goal, new solutions are being born every day. Cryogenic control systems, which once took up entire rooms, are being miniaturized to fit inside compact packages. Quantum processors are being linked through quantum interconnects, allowing distributed computing across multiple chips. And AI-driven calibration tools are being developed to fine-tune each qubit's behavior in real time. You might be wondering, when will we get there? When will we hold a practical, fault-tolerant quantum computer in our grasp? The answer isn't easy. Some experts say within the next 5 to 10 years. Others urge caution, pointing to the monumental engineering challenges that remain. But the momentum is real and growing. Take IBM's roadmap, for instance. In 2021, they launched their 127-qubit processor, Eagle. In 2022, Osprey followed with 433 qubits, and by 2024, they introduced Condor with over 1,000 qubits. Each step brings us closer to machines capable of solving real-world problems, designing new materials, optimizing supply chains, understanding climate systems, maybe even decoding the mysteries of consciousness. We're witnessing a once-in-a-century transformation, not just in technology, but in how we think about thinking. Quantum hardware is the bridge between the abstract and the applied, the mystical and the mechanical. It's fragile, fickle, and full of promise. But hardware alone isn't enough. Just like the earliest classical computers needed new programming languages and operating systems, quantum machines need new ways of speaking and solving. So, what does it mean to program a quantum computer? What kinds of algorithms can bend reality to our advantage? Imagine you're standing at the edge of a vast, uncharted ocean. The waters are filled with strange creatures, hidden islands and currents that defy the normal laws of nature. You're holding a map, but this isn't just any map. It's a blueprint for a new kind of navigation, one that can cross this ocean faster than anything that's ever existed before. This is the world of quantum algorithms, where the rules are different, the methods strange, and the results potentially world-changing. The story of quantum algorithms begins in the 1990s, when the theoretical physicist Peter Shor dropped a bombshell into the world of cryptography. Shor's algorithm, which could factor large numbers exponentially faster than the best classical algorithms, showed that quantum computers could crack encryption methods that protect everything from bank transactions to classified government data. In a world that relies on the security of its digital communications, this was a game-changer. Imagine a hacker with the ability to break any code in mere seconds. Shor's algorithm didn't just demonstrate quantum superiority, it ignited an arms race. If quantum computers could break encryption, they could reshape the digital world. But for now, Shor's algorithm exists in the realm of potential, far beyond the reach of current quantum hardware. Still, it serves as a powerful motivator. If we can solve the issues of quantum error correction, decoherence, and scalability, the implications of this algorithm are staggering. But for now, quantum cryptography is one of the many fields awaiting its day in the sun. Another groundbreaking algorithm to emerge from the quantum frontier is Grover's algorithm, developed by Love Grover in 1996. Grover's algorithm offers a way to search through unsorted data faster than classical computers can. If you've ever had to sift through millions of files to find the one you need, you'll appreciate Grover's brilliance. While classical computers need to check every file one by one, Grover's quantum search algorithm can find the target in roughly the square root of the time. For example, If it takes a classical computer 1 hour to search through 1,000,000 records, Grover's algorithm could do it in just 30 minutes. For 1,000,000,000 records, it would reduce the search time to a mere 32 minutes. But these are just the appetizers. The real feast of quantum algorithms lies in their potential to revolutionize entire industries. Take quantum simulation, for example. Classical computers are already struggling to simulate large molecules and complex chemical reactions. Why? Because the number of interactions increases exponentially as the system grows, creating a computational bottleneck. This is where quantum computing shines. Quantum systems are inherently good at modeling other quantum systems. Imagine simulating the behavior of complex proteins in a drug discovery process. With quantum simulation, we could unlock new treatments for diseases in record time, tailoring drugs to our exact biological needs. But let's pause for a moment. How does quantum simulation actually work? Quantum mechanics operates on principles of probability. Unlike classical computers, which use deterministic rules, quantum computers use probability distributions. When you input data into a quantum system, the qubits don't just represent a single solution. They represent all possible solutions at once. As a result, quantum computers can test many different possibilities simultaneously. This ability is crucial for simulating molecules or materials at a quantum level. They can model the behavior of electrons in a molecule, how they interact, and how that influences chemical reactions. This is an incredibly complex task for classical computers, but for a quantum computer, it's a natural fit. The potential for quantum simulation could redefine entire industries, especially those that depend on chemistry and materials science. The creation of new materials for everything from batteries to solar cells could see an enormous leap forward, as quantum computers explore the chemical space in ways classical systems never could. Energy storage, quantum chemistry, and materials engineering are just some of the fields that could experience a quantum renaissance. Then there's optimization, the process of finding the best solution from a large set of possible solutions. In a world where businesses juggle supply chains, logistics, and manufacturing systems, optimization is king. However, finding the best solution to a complex optimization problem is often a Herculean task for classical computers. Quantum algorithms can help here too, with approaches like quantum annealing and variational quantum eigensolvers. These algorithms take advantage of quantum superposition and entanglement to explore large solution spaces much more efficiently than classical methods. Imagine a logistics company trying to find the most efficient way to deliver packages to millions of addresses. A quantum computer could evaluate all possible routes simultaneously, drastically speeding up the process. And then there's machine learning, one of the most promising applications of quantum computing. We already know that artificial intelligence is transforming industries like finance, healthcare, and entertainment. But as AI grows more complex, it's hitting the limits of classical computing. Quantum computers can help by processing exponentially larger datasets and creating more powerful models. Quantum machine learning is still in its early stages, but its potential to accelerate AI, enhance data analysis, and unlock deeper patterns in data is immense. For instance, a quantum-enhanced neural network could train faster and more accurately, while quantum clustering algorithms could find patterns in data that would be too hidden for classical systems to detect. Now, you might be thinking, this sounds great, but how far are we from realizing these quantum algorithms in real-world applications? The truth is, we're still at the tip of the iceberg. Quantum computers are in what's known as the noisy intermediate-scale quantum (NISQ) era, where the machines are capable of performing some quantum calculations, but not yet with enough qubits or error correction to tackle practical, large-scale problems. Researchers are still working on overcoming the noise, error rates, and decoherence that limit the capabilities of current quantum machines. But the promise is there. It's just a matter of time before the next breakthrough occurs. And when it does, the world will change faster than we can imagine. The race for quantum supremacy is heating up. Companies like Google, IBM, Microsoft, and Amazon are all vying to push the boundaries of what's possible. Meanwhile, nations are investing billions into the future of quantum research. The key players are accelerating toward a common goal, a quantum computer that can solve problems classical computers simply can't. And once we get there, the algorithms we've just begun to explore will become the foundation for a new era of technological innovation. But there's a question hanging in the air: will we be ready? It's the dawn of a new age, an age where computers don't just think, they exist in multiple states at once, can be in two places at once, and compute the impossible in the blink of an eye. An age where the impossible becomes not just achievable, but inevitable. The quantum revolution is here, but what does that truly mean for us? Let's take a moment and imagine the world of tomorrow, a world where the quantum computer sitting in the heart of every major research lab is no longer a rare artifact, but an essential tool in solving humanity's greatest challenges. It's a world where healthcare has been revolutionized, where quantum simulations of molecules are creating drugs tailored to each individual's genetic code, where genetic diseases could be eradicated before they even appear. Diseases like cancer, Alzheimer's, and Parkinson's could one day be understood and cured through quantum-powered medical breakthroughs that were once thought impossible. The complexity of the human body, of proteins folding, enzymes interacting, the myriad of biochemical processes, might finally be within reach of quantum computing's unique capabilities. Imagine, too, a world where the energy crisis is no longer a looming threat. Quantum algorithms could create more efficient solar panels or design batteries that store more energy than any lithium-ion battery today. What about clean fusion energy? Right now, we're just scratching the surface of trying to mimic the process that powers the sun in a lab. But a quantum computer, with its ability to simulate the behavior of every particle in a fusion reaction, could solve the equations that have baffled us for decades. It's not just about theory anymore. It's about making the dream of nearly limitless clean energy a reality. But what about the everyday world? How will quantum computing trickle down to affect us all in ways we can touch and feel? Perhaps one of the most immediately impactful areas will be logistics and supply chains. Think of all the goods that need to be transported, from food to clothing to electronics. The complexity of optimizing these global supply networks is staggering. Current systems are often inefficient, but quantum computers could bring about near-perfect optimization. Delivery times would drop, costs would plummet. The economy could see a seismic shift in efficiency, drastically reducing waste, energy, consumption, and carbon footprints. Imagine a world where every supply chain runs like a well-oiled machine, where quantum computers keep everything from fresh produce to crucial medical supplies flowing seamlessly. It could reshape industries we take for granted, from food delivery to manufacturing to retail. And then there's the realm of space exploration. While current computers help guide us to the stars, they're nothing compared to what quantum computers could do for interstellar travel. Imagine a mission to another star system, an ambitious goal that will one day define humanity's place in the cosmos. Quantum computing could simulate the entire mission in ways we can't even begin to imagine now, optimizing spacecraft trajectories and fuel usage in real time, solving complex problems in seconds that would take today's computers thousands of years. With the combination of artificial intelligence and quantum computing, future space missions might be able to autonomously adapt to unforeseen challenges, much like a sentient being making split-second decisions. Quantum simulations could also help us understand space-time, black holes, and the deepest mysteries of the universe, ushering in a golden age of astrophysics where the cosmos becomes more comprehensible than ever before. But there's also a darker side to this quantum future, a dangerous new frontier. As quantum computing advances, it has the potential to disrupt everything we currently know about security. The same algorithms that can break encryption with terrifying efficiency could be used to compromise financial systems, personal data, and national security. Right now, most of the world's data is protected by cryptography that relies on the fact that factoring large numbers or solving certain mathematical problems is impossible for classical computers. But quantum computers could obliterate that security in an instant. It's already predicted that once large-scale quantum computers are built, The encrypted data we trust today could be exposed in seconds. This could put everything from online banking to government secrets at risk. But here's where a paradox arises. Quantum computing can also provide the solution. Enter quantum cryptography, the next wave of secure communication. Using the principles of quantum mechanics, we could create encryption that is practically impossible to crack. Quantum key distribution, QKD, is already a reality in certain parts of the world, and it offers a way to share encryption keys so securely that even a quantum computer couldn't eavesdrop. In fact, the mere act of observing a quantum system will change it. This no-cloning theorem ensures that any attempt to intercept a quantum message would leave a trace, offering a level of security that classical methods simply can't match. As the quantum age progresses, we will need to rethink everything we know about cybersecurity. What we've built may no longer be sufficient, but quantum tools offer the potential to rebuild even stronger defenses. All of this points to one undeniable truth. Quantum computing isn't just a technological shift, it's a paradigm shift. It forces us to rethink the very nature of computation, knowledge, and even existence. As quantum algorithms unlock doors to new dimensions of possibility, we'll need to rethink the tools we use to understand and shape the world around us. It won't just be an advancement in computers, it will be an evolution in how humanity interacts with reality itself. But we stand at a precipice in a moment of uncertainty. The quantum revolution, like the industrial revolution before it, will come with both immense benefits and new challenges. The pace of change will be overwhelming, and yet it's up to us to guide it, to make sure it's used wisely, ethically, and in service of humanity's greatest good. So what happens next? Will quantum computing remain a theoretical marvel, or will it become the foundation upon which the next era of innovation is built? The answer, as always, lies in the hands of the explorers, the visionaries, the pioneers, the scientists, engineers, and dreamers who are already laying the groundwork for a world we can only begin to imagine. Now it's your turn. Will you be one of the first to witness the birth of this quantum age, or will you wait until it's too late to catch the wave? If you're ready to join us in the discovery of the future, don't forget to hit that subscribe button, because the journey of 1,000 quantum leaps begins with a single click. Like, share, and comment below. Let's continue to explore this brave new world together. The universe is waiting. Are you ready to unlock its secrets?